So in this recording, I'm going to focus on the vector spaces. I'll just repeat them again. At this time around, we're going to repeat them with examples only, and maybe the theorems. Okay, when it comes to the axioms of vector spaces, we know that we've got the first 5. The first one is closure under addition. The second one is, so it's U plus V must be an element of V. But that is just a vector, right? And this U is just a vector. And then U plus V is equal to V plus W. This one is the associativity property, your commutativity, this one. So in most cases, if the commutative one holds, even the associative one is going to hold A3. And this one is associative. Then we come to the additive identity. So here you will have U plus 0 is equal to U is the same as 0 plus U. And you also have the additive inverse. So here U plus negative U must be equal to 0. So obviously you'll find your additive element on the step on A3. And then this is the same as negative plus U. We know this is true. Then we have axiom 6, you're going to say SM1. You'll also have SM2, SM3, SM4, SM5. So the first one is closure under scalar multiplication. You'll have sigma times U must be an element of V, whereby alpha is an element of your field. And then we also have what? Actually, this will it will already be specified on the definition when you define what is a vector space. Remember, the axioms are also part of your definition worth 10 marks. And then alpha U plus V is equal to alpha U plus alpha V. Then this one is the distribution law. By distribution law, then you'll have now add the two scalars on the SM3, and then you'll have U. This will be equal to alpha U plus beta U. And also when you have got the product of two scalars multiplied by a vector, this will be equal to alpha beta U. This is by associative property. And then the last one is the scalar identity. 1 multiplied by any vector is equal to U. Say same applies if you are having this vector. This is just an example. If this is your U, the answer we're expecting to get 0, 1 in this case. So now an example. Such that x is an element of real numbers with the operations is equal to x plus y over 1 a x. So here you have got a vector that is defined in two ways. You've got a vector defined in a form of addition and multiplication. So when you write your solution, let me add, you decide whichever you're going to prove, whichever axiom you want to start with, but usually I prefer starting with the order as it is. So obviously this is scalar multiplication, and then this one is scalar addition. So your solution, you can say let uv be an element of v, right? And then we know that u, we're going to say let u be equal to x comma 1, which is this, and then we let v be equal to y and 1, whereby y is an element of, we know that y is an x and y are element of real numbers, so such that x and y are element of real numbers. That's how the operation is defined. X is an element of real numbers. Also, y therefore must be an element of real numbers. Then now we can start with A1, which is closure under addition. Then you'll say u plus v is equal to, so you'll say you know what your u and our v is y1. So when we perform addition, our addition is defined in that way. So it means you'll say x plus y, then 1 is fixed. If you check, 1 is fixed. So even here we're going to fix 1 like this. Then we know x plus y is an element of real numbers. Then we can say u plus v is an element of the vector space V. So closure under addition holds. Then I come to axiom 2. Where here we must check what? We must check if commutativity is going to hold. U plus v is equal to v plus u. So you can say the left hand side, you know it's u plus v. We already have the answer of this one is x plus y comma 1. Then for v plus u, we know that you're going to perform y1 plus x1. Then this will give us y plus x. Then you fix 1. So this is our answer. So this is commutative. You see that the left hand side is equal to the right hand side. So we can say that u plus v is an element of v, and then you can say hence associativity holds. Associativity property holds. Property holds. Then now I'm going to come to the next part. I'm going to now skip axiom 3. We have done commutativity. Oh, yeah, I was supposed to say commutativity holds. I'm going to skip associativity, right? Because they will have to introduce new variables, but which is also not a problem. Hence, here I was supposed to say commutativity holds. So we're going to skip axiom 3 because it was also going to hold. Know for sure that it was going to hold. And then axiom 4, the additive identity. That is to check the additive identity. So I can say let 0 be equal to, since so you come back here, you see that your vector was defined like this: element comma 1, element comma 1. So it means even here you will say element comma 1. So we're letting 0 to be this. And then, or you can say e2 comma 1, it's up to you. Then you can say then u plus 0. We know that we're expecting to get u when we add this. Or perhaps let me remove these arrows. U plus 0, vector, you must get u. Now our u, we know that is x1. Then we are letting 0 to be this. This is x1. So this implies that we said when we perform addition, we'll get x plus e2. Then we fix 1. So this is equal to x comma 1. So this means that this is equal to that. So we'll have x plus e2 is equal to x, and 1 is equal to 1, right? So that's not a problem. We're not going to write 1 equal to 1. Then this will imply that this will cancel. E2 is equal to 0. Therefore, 0. Remember that 0 was E2 and 1. So this will imply that 0 is just equal to 0 and 1. And since this is an element of real numbers, we can say that additive identity holds. This is still an element of real numbers, and also this one is still fixed. Then I can check additive inverse, which will be SM. Oh, it's A5, right? A5 done with A4. So I'm going to say we know that with the additive inverse, generally we have this. So we can say, and we know that u is equal to x and 1. So I can say let negative u be equal to x1 comma 1. Or we can actually just yeah, because we want to actually verify what we're going to get. We can say let negative u, we multiply this by negative, you'll get negative. So we cannot multiply this one by negative. Hence, I wanted to first, but we can even write it like this. It's still fine. This is still an element of real numbers. Then this will imply that I'll have x comma 1 plus negative x and 1. So already know what is our identity element, 0 and 1 from the previous step. Then this will imply that I'll just have a x plus negative x then and 1 when we perform the addition of this. So this will imply that I have what? This will give us 0 and 1 is equal to 0 and 1. So we can now conclude, therefore, negative u is equal to negative x and 1. Negative x is an element of real numbers. Then we come to, can check which property. Let me see. We can check, okay, we can check still on the same question. Now I want us to focus on we've checked the commutativity, we've checked these two. I'm going to skip the associativity property. We're going to go straight to SM1 and SM2. So let's start with SM1. We said with SM1, we're checking for closure under scalar if it holds. So here we're given that when you've got a scalar times your vector, you'll get kx comma 1. That's already given. So we want to check if that holds. We're given that this condition, if you multiply a 2, a scalar times a vector, you'll get kx, and then 1 is fixed. So I want us to put that there. So we know this already. So we just want to verify that when you multiply two scalars, suppose you multiply k with u, we're expecting to get, according to our axiom, we're supposed to get this must be an element of our vector. So we're expected to get ku being an element of our vector. So that's how the axiom is. So in this case, it means that this will be equal to k multiplied by u, comma 1. And we already know what is u. So our u is x and 1. So you'll have x and 1 here. And this will be kx, k, 1. So our 1 is still fixed. So we don't have a problem there. So we can say, therefore, and we can see that if I take out a k here, I'll be left with x and 1, and 1. And this is just k, u, and 1. So I'll just go back there. So we can say that closure under scalar multiplication holds. And we can check because SM1 then come and check SM2, which is the distribution property. So we can say let alpha and beta, or we can use another variable. Let me say let alpha m be any scalars in the vector field. You can say where alpha and m are an element of a field. Then alpha plus m and your vector. This must give us, when you multiply, remember this is multiplication. When you multiply this, we are expecting to get a fixed 1. So we're expecting to have 1 here, and then this must give us alpha plus m and then u. So this is how remember our vector is defined in this way. X, they said this is equal to xk1. So this is how our vector field was defined. So even ourselves are going to define it in this way. Then now we can multiply with our u. You'll have u alpha plus um1. So this is the same as, so this will be the same as alpha u 1 plus, when we distribute, alpha m and 1 by the distribution property. You must indicate here by the distribution property. Then this will take, you can take out what? You can take out alpha, and then this will be this. Oh, remember, this will be the same as alpha u, and this will be the same as, by the definition, this will be the same as u. Our scalar is m u by definition of our vector field. So we can clearly see that the distribution property will hold. So obviously, even if you check for SM4, which is the distribution, which is the associative property. Associative we'll expect it to also hold, but let's check it. Then you'll have alpha times u plus v. Then this is alpha dot, we know our u is x1, our v is y1. No, this is the one that I'm doing here is not a associative. The associative one should be like this. So the one I was doing here is distribution properties. The one that I was doing. So let me remove this. The one that I was doing up there, SM2. So remember, I've got SM2 and SM3. With SM2, you are multiplying with a scale outside, but on SM3, it's you are multiplying with a vector, but on SM3 you are multiplying with a scale. You are multiplying two vectors with a scale. And then here on SM4 will be multiplying two scalars, alpha m. We're going to be multiplying it with a scale, and this will be alpha m. This is x1, and this will be the same as alpha m x. Then one is always fixed. Remember that. Then this will be the same as alpha. If I take out alpha, it means this will be alpha what? Alpha multiplied by mx comma 1. You'll be left. This is by the definition of our vector space. Then now this implies that I will have alpha into, if I take out, and then this also by definition will be m dot x1, and then this now will become alpha m dot x1, which is just alpha m dot u. So you see that this is the same as the left hand side. So this is what we're trying to achieve. We're trying to achieve this. So I've managed to get that here on this step. So this is our right hand side. It's equal to now the left hand side. So we can say that we can also further on continue to check for the last axiom SM5, which will be 1 times u, but we know that this one will just be what we know our value of u is x1, and this will just give us 1 times x, 1 times x, comma 1, then this will just be x1, and this is just u. So also this one, it holds. So we must try to always check all of them. That's the key part. And sometimes you'll have to use counter examples in order to show these things. So let me just take one more example, and then I will do something different after this. Example 2. Suppose you have vector v, a, b, c, d, an element of M22 such that a plus d is equal to 0. So we're going to let a be equal to a, b, c, d, and I can let b be equal to e, f, g, h. Then we can start checking that property, all the axiom. Then A1, we know that we are going to check for closure under addition. So here we're going to check for closure under addition. So it means we'll be adding a plus b. This will just be a, b, c. So you'll be having something like that. Then this will give us a plus e, b plus f, c plus g, d plus h. So on this step, this is still an element of what? Of M2 by 2 matrix. Now from the definition that when you have a vector which is a 2 by 2 matrix, when you add, you must get what? 0 when you add the opposite vectors. So it means here I will add a plus e plus d plus h. This is equal to 0 by definition of a vector space. You can say by definition of a plus d equal to 0 in the vector space V. So this implies that a plus e must be equal to what? A plus e must be equal to 0, and this also implies that a plus h must be equal to 0. If we further manipulate this will imply that a is equal to negative e and d was going to be equal to negative h. That's what it implies. And then we can say, therefore, closure under addition holds. Then number 2, axiom 2, we can say, want to prove associativity, right? We'll say let C be equal to Wx, Yz. This is an element of 2 by 2. And then we know that if we are having this, we are expected to get A plus B plus C. Then A was A, B, C, D. B is C, F, G, H. This was my B. Then plus C is the one that I said let it will be like this. So here we want to try to check the left hand side if it's going to be equal to the right hand side. So in this case, this in the meantime is our left hand side. So I want to check if this is going to be equal to CF GH, and I have space here. So and then now I'll go to also include C. So our C is outside the brackets WX, YZ. Obviously, if we start with the left hand side, A, B, C, D, we'll get C plus W, F plus X, G plus Y, H plus Z. And then this is equal to, if this is still our what? Our left hand side, né? Then also you will add this A plus C plus W, B plus F plus X, C plus G plus Y, D plus H plus Z. So this is an element of that. Then you'll also check your right hand side. C F G H. So obviously you are having A, B, C, D. This will be C plus W, F plus X, G plus Y, H plus Z. X, C plus G, Y, H, Z. If you compare the left hand side and the right hand side, you realize that they are equal. So associativity holds. The law of associativity holds. So I'm going to quickly now skip. So this was going to be a vector space. You'll just confirm. You'll check also SM5. Obviously, you'll check the if when you multiply 1 times u, if you are getting u. In our case, we're using a, you'll still get a. Obviously, 1 times. Obviously, this will be 1 times any vector. So this is a scalar 1. Obviously, you'll still get a. So you'll also check the other axioms. Your SM1, SM2, SM2, SM3, SM4. But at the end, you should get that this is a vector space. Then here we've got some proofs. We've got actually we have 4 proofs that you must know how to prove, which is these ones. But for now, I'm going to add for this recording. I'm going to add these ones. The cancellation law. proofs to know for test one. The first one is the law of additive identity. U plus V must give you U. The second one is additive inverse. U plus V must give us 0, and therefore, thus V must be equal to negative U, where U, V is an element of V. The third one is the law of cancellation law. U plus W will give you V plus W. And then therefore U must be equal to V for all U, V being in V. So let's start with the first one, 1.1, the additive identity. So I'm going to say let 0 be an additive identity of V. Then U plus 0 prime must be equal to U, and this will be equal to 0 prime plus U by law of associativity. We can just say associativity. Now, 0 prime will be equal to 0 prime plus 0. Since 0 prime is an additive identity, we said let 0 prime be an additive identity. Is an additive identity. So an additive identity, when you add an additive identity with 0, you must get that additive identity. That's what it means. Then now we can say 0 prime is equal to, this will be 0 prime. Okay, let's open a page here. You can now say that 0 prime will be equal to 0 prime plus U plus negative U by, this is by additive inverse property. Then this will be 0 prime is equal to 0 prime plus U. So here we're going to use associativity property. So you must always write these results by law of associativity. Then this will be U plus negative U. Then this is 0, 0 prime. Then I come to the second one, which is the additive inverse. Now I'm going to say suppose U is an element of V, it has got two additive inverse, negative U and negative U prime. Then you'll say negative U prime will be equal to negative U prime plus 0. We know that 0 is an additive identity. You must always try to write results. Then this will be implies that negative U prime plus U plus negative U. This obviously is by what? Law of additive inverse. Then this will now give us negative U prime plus U by law of associativity plus U. And this will give us 0 plus negative u. Negative u, therefore this implies that negative u prime will be equal to negative u. Wanted to get what? This was the additive inverse proof, ne? That v is equal to negative u. So we're supposed to get v is equal to negative u. Let me see what happened. What happened here? Okay, for now I'm going to leave it. I'm going to leave this property here. I think I will have to explain it why I wrote it. So we'll check it. I think maybe here on the guide they have explained it properly. Let me see. They wrote it. Okay, it's fine. I'm gonna do it some other time. So the last one, but we should be getting on the final answer here, we should be getting v equal to negative u. We should be getting this. Okay. No, or u equal to no. This is yeah, this is correct. It is correct. So you'll also check it. Then 1.3, it is correct. We're getting, remember when we add negative u prime plus negative u, this is equal to 0. Remember that this is the same as u plus negative u is equal to 0. Yeah. So we can now move to the uniqueness or the cancellation law. So it's also called uniqueness of additive inverse. So when you add u plus w, it's equal to v plus w. So we must get u is equal to w. This is what we must get at the end. Ne? U is equal to, it should be u is equal to v. Yeah, u is equal to v, not w equal to v. So the proof will be like this. So you're going to say let u v be an element u. Let u v w be an element of v such that u plus w is equal to v plus w. Then now you're going to introduce for me a negative w here. Just introduce it and then you write the reason. You say by additive. Actually, this is by what? Cancellation law. I forgot how you, but you can write this one for now by additive inverse. Remember, if I take this to the right, it will give us 0. So we can just say by additive inverse. And then this now will be u plus w plus negative w, v plus w plus negative w. Then this will be u plus 0, v plus 0, then u is equal to v. Then we are done. Then there is also the one whereby you must prove This one is another proof. You're going to suppose alpha v is equal to 0. Then you must show that either alpha is 0 or v is 0. So we know that v will be equal to 1 times v in general by the scalar identity property. Now, suppose that we let alpha have a what? An inverse. So let's say if alpha is not equal to 0, then alpha has an inverse. This will imply that you'll have v is equal to alpha times 1 over alpha times v, because this will still give us 1. Then you will say this will now be equal to 1 over alpha v. And we know that this should give us 0 by hypothesis. So you are going to assume, you see here we say suppose this is equal to 0. So I'm going to assume that it is equal to 0, and then this is equal to 0. And I think we also have another one. Then we also have another proof, but maybe I should stop here for now. Let's see. Okay, let me see if we can actually also do this one. Show that zero u is equal to u for all u be an element of V. So you will say let 0 be an element of the field, since 0 is acting as a scalar, such that 0 is equal to 0 plus 0. Then you will say let u be an element of V. Then by the distribution law of scalar, this will imply that I'll have 0u. I will just multiply by u both sides. And this will be equivalent to 0u plus 0u. Then this will be 0u plus minus 0u. And I take this one to the... No, here I just introduce a negative 0u. You just add it like this. The same way with the previous proof. Now this will give us 0. And this one will give us 0 on the left. Then now I just have 0 is equal to 0. We have managed to show this. So I'm going to stop here.